Hi, kids. All right, here is Basic Circuits Part 2. Look, it's in 3D. Delint, delint. This little video is going to be about electric current. Okay, so let's talk about, well, first, the symbol for electric current is a capital I. Okay, why do they use I? Well, in the next video, I'll give you a very nice reason why they use I. Okay, but for right now, we're just going to say, hey, they use I. Well, what is electric current? Okay, electric current is the rate charge, if you like, goes by, or I don't really like the word moves because it's really more than just moves. It's really the rate charge is going by, okay? So anytime we talk about rate, okay, that means that I really is Q divided by T. All right, so make sure, again, you can see that and find that equation on your formula sheet, okay? Well, what is I measured in? I is measured in amps. That's the unit, okay? Which is going to be abbreviated to capital A, okay, for amps. So if we're talking about an ammeter, it's measuring amps, which is measuring current. And an amp really is a coulomb per second. That's going to be important, especially in a couple videos from now when we talk about power. Okay, but it is. An amp is a coulomb per second, okay? But make sure, again, this is just kind of the basics, like what current actually is. Now remember, current flows through, this is so important, the circuit. And actually the word circuit means to go around. So like you can think of these charges literally moving around the circuit, okay? Because that's really what they do. Let's see, it flows through the circuit. The relationship, okay, between voltage and current is this, and this is actually how you will see it on your equation sheet as well. Okay, this is called Ohm's law, which is the relationship between voltage, resistance, and current. The reason the College Board writes it like this, as opposed to the very nice way, which later on, is that they are saying current depends on voltage and resistance. So if you have a bigger voltage, bigger potential difference, you're going to get more current. If you have more resistance, you're going to get less current. Because remember, resistance resists current. So more of this, less of this. Okay? Hopefully that makes sense. If I was to show you a circuit, a real basic circuit, and let's just say, hey, I have a battery and a resistor here. That resistor could be a light bulb, a heater, a motor, whatever. If I want to measure current, I have to put my meter as part of the circuit. So let's say I have a meter right there, and I'm going to call it A1. Well, that means the reason I have to do that is the current comes out. Now, conventional current is what we're going to be talking about. Conventional current flows in the direction that positive charge would go. In reality, electrons are actually moving, but when they tried to figure this all out, hundreds of years ago, they kind of screwed that up. So it's conventional current. It's the direction that positive charge goes, which is this way. Notice I'm not saying protons, I'm saying positive charge. Like this. Then if you look, hey, current goes to here, it goes through my meter, and then it goes through this resistor and back over here. Well, if I have another meter over here, okay, that if you look, these two meters have to measure the same thing. Because whatever current comes out here has to go there, has to go there, has to go there, and then has to go there. Okay? So the current in this meter and this meter are going to be the same. Why are they going to be the same? Really, it relates to what is called conservation of charge. Okay? Well, what is conservation of charge? Well, you're not going to create or destroy charge. So if charge comes out and goes there, it has to keep going, and it has to keep going, and it has to keep going. Why? Because there's only one way for the charge to go. Okay? There's no junction, there's no breaks, there's no different paths. So that means the current everywhere has to be the same. All right, that's good. And then if I have, let's say I have a slightly more complicated circuit. So here's my battery. Let's say I have a meter here. I have a resistor here. I have another meter here. I have a resistor there. Resistor. And let's say another meter here. And then I have another meter here going to the battery. Okay. So this is where, okay, the junction rule, hopefully we can see that okay. That if you take a look, well, what is the current going to do? The current's going to come out, it's going to go through this meter, and then it's going to go through this resistor, and then it's going to come here, and then it's going to split. Okay? Some of the current's going to go this way, and some of it's going to go this way. Well, how do you know how much current goes which path? Well, let's say this was 10 ohms, and this was 40 ohms. Well, guess what? Twice as much current is going to go in the bottom path. Why? Because it has half as much resistance. Okay? It's resisting current. And then it's so the current would come out, go here, split. Okay, you would have twice as much go here, half as much go there, and then it comes back together and goes here. So if you were to write an equation relating this, well, that means A1 would have to equal A4 because the current goes here and it splits, which would have to equal A2 plus A3. Hopefully that makes sense. Okay, this is called the junction rule, which really just states whatever current comes into a junction has to go out of a junction. Duh. Okay, like just conservation of charge. So whatever current goes into a junction has to come out of a junction. So let's say I have something like I have a junction. And I have, 10 amps coming in, and maybe 2 amps coming in, and then this is going to be 5 amps coming out. So then it's like, hey, figure out what's happening over here. Well, how much current is coming into my junction? Oh, well, 10 plus 2. 10 amps plus 2 amps. How much current is coming out of my junction? Oh, well, 5 amps. Oh, well, this is 12. Shoot. I can't, destroy charge. So that means I have to have 7 amps flowing out of my junction in order for that to be true. Okay? That is how current works. Hopefully that makes sense. Bye, kids.